Hello friends, welcome all of you. Now after the discussion about the Colruy's law, Debye-Hakelon-Sanger equations, now the next thing that we have to discuss, that is measurement of conductance. Measurement of conductance. Basically, we know that the conductance measures in the terms of resistance, but the resistance can be measured accurately for the solid conductors, or we can say metallic conductors, not for all the types of conductor. Not for all the types of conductor. And the main problem faced during the determination of conductance of electrolytic conductors, because the electrolytic conductors present in the liquid form, aqueous solution. So that problem is solved by the use of Wheatstone-Bridge principle. Wheatstone-Bridge principle. And according to this principle, if we can measure the resistance of unknown electrolytic solution, then we can measure its conductance also. And in in Wheatstone-Bridge principle, you know very well, there are four resistance, and in these four resistance, all these are connected through in the series. This is the basic principle of Wheatstone-Bridge. We are just discussing what is the Wheatstone-Bridge principle, and the Wheatstone-Bridge principle we are using here to measure the resistance of unknown electrolytic solution, that is generally R2. This is R1, that is variable resistance. This is R2, this is another resistance R4, and this is R3. So when we are deal with this Wheatstone-Bridge principle, the ratio of R1 R2 is equals to R3 and R4. Our target is to determine R2. This is unknown. Unknown means whose conductance we want to measure. Here that is electrolytic solution, so we can say this is the resistance of electrolytic solution. So R2 is equals to R1 R4 upon R3. By the measurement of the resistance of unknown conductor, we can determine its conductance, because conductance is the reciprocal of resistance, and the electrolytic conductance can be measured with the help of Wheatstone-Bridge principle, and this is the Wheatstone-Bridge principle introductory part. Okay, but there are two problems if we use such type of arrangement. What? First thing is that, like the metallic conductor, electrolytic conductors cannot be connected in this manner, because they are in solution phase, and a solution cannot be connected with the solid metallic wire directly. So this is the basic problem. Second thing is that in this we are using we can't use direct current also. Why we can't use direct current also? First thing is that if you use direct current for the measurement of conductance, the cell the cell which we are going to construct from the electrolytic solution will be behave like electrolytic cell, means its chemical substances start to decompose, and when the decomposition is there, cell will not work there. What is the concept of cell here? To measure the or to use the electrolytic solution in Wheatstone-Bridge principle, it is necessary to convert that electrolytic solution into a conductivity cell. In the conductivity cell is a simple cell which have two inert electrodes, generally platinum. The platinum wire or platinum electrode coated with the finely divided platinum black, means the electrode coated with the platinum black material. So it is completely inert. Okay, so we use platinum electrodes to construct a conductivity cell for the given electrolytic solution. Okay, so this is the problem we face during the use of direct current for the electrolytic solution. And the second problem is that electrolytic solution cannot be used as such, which is required for Wheatstone-Bridge principle. Means here we are using directly resistance, we are directly connecting the unknown conductor with metallic wires. This arrangement is not possible in the electrolytic solution. To overcome this problem, we convert that electrolytic solution into conductivity cell. And the first problem, which I have already explained, that we can't use direct current here, because when we use direct current here, then the conductivity cell or the cell which we have constructed will behave like the electrolytic cell. So to overcome these two problems, we use here meter bridge to determine the resistance of unknown electrolytic solution. In this manner. This is point A, this is the point B, this is point C, and this is the point D on, sorry, please pardon. This is A, this is B point, this is C, and this is D. Okay, this B point connected through a jockey, and in the first part we use here a resistance box, to select an appropriate resistance so that we can get null point by the use of jockey on this meter bridge. And this is the resistance of unknown electrolytic solution which converted into conductivity cell. So this is the conductivity cell. This is conductivity cell. So this is the arrangement. Okay, or we can change also it. Suppose this is resistance fixed and this is unknown resistance, that is X. Okay, so the ratio of the known resistance R and unknown resistance X is equals to the length of AD upon the length of CD. By putting the value of the resistance of resistance box which we have used to get the null point on meter bridge, X, this is the resistance of unknown electrolytic solution which converted into conductivity cell, then AD, the length between A and D, CD, the length of C and D. By putting the value of all these three, we can get the value of X. As soon as we find out the resistance of conductivity cell, it will convert into conductance. So in this manner, we can measure the conductance of electrolytic solution.